is Walid, roll number 24I0728, and today we'll present our discrete structures project analyzing price similarity networks across 17 Pakistani cities using consumer price index data spanning 31 months from March of 2023 to October of 2025. Our objective is to identify which cities have similar pricing patterns by constructing networks where cities are nodes and edges represent similarity in their price vectors across 7 product categories, which include food staples, fruit and vegetables, meat, poultry and dairy, oils and condiments, clothing, non-food essentials, and utilities. CPI data reflects economic conditions, inflation patterns, and market dynamics. By using cosine similarity, we measure how aligned price movements are between cities. Network analysis then reveals which cities are central hubs in the economic network, helping identify price leaders and market influencers over this 2-year period. This project applies core discrete mathematics concepts such as relations, graph theory, partial orders, and centrality measures to real-world economic data. For each city, we constructed a CPI vector containing prices for all items in a given category and the time period. Our dataset has 17 cities, 7 categories, and 31 monthly periods, creating 217 distinct networks to analyze. A critical preprocessing step was using z-score normalization per item across cities. This is essential because normalizing per city would make all the cities look 98% similar. By normalizing each item's prices across cities, we capture which cities move together relative to the national average for each product. We computed pairwise cosine similarity between normalized city vectors using scikit-learn's cosine similarity functions. This measures the angle between two city price vectors. A similarity of 1 means identical price patterns, while -1 means opposite patterns. Edges are formed only when similarity exceeds a certain threshold. We tested multiple thresholds using food staples data from March of 2023. A threshold of 0.6 gave us 9 edges, a threshold of 0.7 gave us 6 edges, and a threshold of 0.8 gave us 4 edges. Higher thresholds revealed only the most tightly coupled cities. We implemented 4 weighting schemes to aggregate centrality scores. Scheme A is equal weights, Scheme B is correlation based, Scheme D is entropy based, and Scheme E is interactive sliders. Additionally, we implemented category importance weighting to create a national city ranking by aggregating across all 7 categories. Food staples and grains have an importance of 25%, utilities and transport 20%, meat, poultry, and dairy 15%, and other categories 10% each. This produces a single national score per city reflecting overall economic importance.
We start by loading the clean dataset with pandas. Our data contains 26,767 records. We create a period column combining year month for temporal analysis. For computing all pair similarity, our Tor function build the graph from similarity takes filtered data, creates a city into item pivot table, normalizes per item, then computes cosine similarity for all city pairs and builds a network X graph with edges where similarity is greater than the threshold. And the key data structures we have used include pandas data frames for tabular CPI data, net worth X graphs for net worth representation, frozen set for immutable edge sets, and NumPy arrays for similarity matrices. We compute four centrality metrics for all 217 networks. Degree, which is the number of direct connections, closeness centrality, which measures average distance to all other nodes, betweenness centrality, which measures the frequency of the node on shortest paths, and eigenvector centrality, which measures importance based on the connections to other important nodes. Results are saved to a centrality store CSV with 3,689 rows. For visualizations, we use Plotly for interactive geographic maps with time sliders, Matplotlib and Seaborn for heat maps and bar charts, Network X layouts for graph visualizations, and IPY widgets for interactive controls. The interactive dashboard visualizes networks on a Pakistan map. We can select different categories, different timelines, and different thresholds, and it will show the connections between cities that form in that month for that category and for that threshold. We can also play a slideshow. We compare different cities based on the four weighting themes: Islamabad, Rawalpindi, Gujranwala, Faisalabad, and Multan ranked mostly on top. Rankings are robust despite mathematical differences in weighing. This 17x17 heat map shows city-to-city similarity for food staples in March 2023. Darker red means higher similarity. We see clusters Islamabad and Rawalpindi pair strongly. Karachi and Hyderabad also pair, showing regional economic ties. Now let's demonstrate our fourth weighting scheme, the interactive custom weights. This allows users to manually adjust how much each centrality metric contributes to the final ranking. Notice how the city rankings update in real time. This gives researchers flexibility to test hypotheses about which network properties matter most for them. These four line charts track centrality metrics over 31 periods for top cities. Degree centrality: Islamabad maintains highest connectivity. Betweenness varies as cities alternate as bridges. Closeness is stable, whereas Eigenvector centrality shows Rajawala occasionally surpassing Rawalpindi. The key pattern is that specific metric values change. The relative ranking remains stable, indicating a persistent economic hierarchy. Now let's look at our discrete math application, Hasse diagrams showing temporal partial orders. For each category, we compare edge sets across time periods. If the edges at time t1 are a subset of the edges at time t2, we have a partial order relation. The Hasse diagram is a transitive reduction. We remove redundant edges to show only the essential ordering relationships. This verifies our network satisfies POSET properties, which are reflexivity, antisymmetry, and transitivity.
Despite using three different mathematical weighting approaches, equal weights, correlation-based, entropy-based, the top five cities are identical. But why? These cities, Islamabad, Rawalpindi, Gujranwala, Faisalabad, and Multan, are major economic hubs with consistent pricing patterns, high connectivity, bridge positions, and link to other important cities, and their centrality is robust across mathematical formulations. Threshold analysis reveals low thresholds form city clusters based on regional proximity. The higher thresholds isolate core pairs like Lahore Faisalabad and Islamabad Rawalpindi. Network density decreases exponentially with the threshold. Some cities become isolated at high thresholds. Centrality scores change because the supply shocks affect specific products like seasonal fruits. Regional policies create temporary price divergence. The transportation costs fluctuate and the market integration varies by category. Temporal analysis using Hess diagram shows 4 categories exhibit partial order structure. 3 categories shows no ordering. Oils and condiments converges to minimal network in April 2025. The meat shows a complex evolution with 10 Hess edges. Overall variance, if we talk about, there is a moderate one. Top cities maintain positions, but the peripheral cities show higher volatility. Our key findings: Islamabad is the most central city across all weighting schemes and time periods. The rankings are robust, however. The threshold choice critically affects network structure and city clustering. Category specific pattern exists. Oil utility is highly correlated, while the clothing fruits more variable. Partial order analysis reveals some categories evolve systematically, others chaotically. Limitations: national coverage is incomplete as the data is limited to 17 cities. Monthly granularity may miss weekly price fluctuations. Cosine similarity assumes linear relationships, and the missing data handled by mean imputation, which may bias results.